We have to put something in the vaccine that causes a little bit of halchal. All of us will remember since childhood that when we take a vaccine, that part becomes tender, it swells up, there is inflammation. We are building a mimic of an infection. It will, if it does what the infection does to some small limited degree, then there will be a good immune response. All of us get that. There are no exceptions to that. What is that created by? As I said, it's created by cytokines being released locally. Now, some of us make a little more cytokine, some of us make a little less cytokine. All of us will get that local little bit of tenderness, a little bit of swelling, all of that. So all of us will respond by making a good immune response. However, depending on whether some of us have made a little more of these cytokines, the cytokines are really supposed to have a local effect. But if there is enough made, they will overflow into general circulation and then they will have body-wide effects. And those body-wide effects are what lead to fever, that lead to feeling very unwell, malaise as medical people call it.
Hey, hi, welcome to Biotech Talks. In this episode, Dr. Rath has explained how your body fight against COVID-19 infection to keep you healthy. Now, by knowing how my body is protecting me against COVID-19 infection, I get confidence, I get courage, I get a positive attitude, which is very necessary in this awful situation of pandemic that we all are in. And I know regarding COVID-19, all of us have a lots of questions like how vaccination works, what are the side effects of vaccination, why some people show side effects while others don't, why some individuals show severe complications of COVID-19 while others remain asymptomatic. Well, all of that and much more will be explained in this podcast. And I feel very fortunate to meet Dr. Rath, a well-known name in Indian science, currently visiting faculty at IISER Pune and former faculty of National Institute of Immunology.
Hello sir, how are you?
Very well, thank you.
So when pathogen like coronavirus does the infection, what is the response of our body against it?
So we have to think about this from the point of view of when first encounter happens. So viruses will come into the body. Viruses like SARS-CoV-2, which is the COVID-19 virus, come into the body on droplets. So when the droplet comes in, that's loaded with virus particles, the droplet lands somewhere in the lining of my respiratory system, in lining of my nose, throat, my breathing tubes, and so on and so forth. So when that happens, what we are thinking is that it lands on our cells, but it doesn't really. It lands in fluid, because as we are all aware, our nasal passages, our respiratory system is all, there is fluid. We cough it up, we sneeze it out, and so on and so forth. So the droplet lands in fluid. So the virus particle is released into fluid. It has to sink through the fluid, and it's thick fluid. It's not. It's mucus. So it has to sink through fluid to hit the surface of the cell, of some cell, before it can actually even think about sticking to the cell and getting in. During this time, the body already has two possibilities of pre-made ways of stopping the virus particle. One, regardless of whether we have been exposed to that particular virus or not, and that is, remember that the virus is inert. There are no biochemical processes going on in the virus particle. So if the virus particle is damaged, there is no way for it to get repaired. So it's going to be lost as far as the virus is concerned. And all our body fluids have enzymes that do this, have protein breaking enzymes, proteases that do this. So proteases in body fluids are one initial pre-made barrier to virus infection. On the other hand, if we have been exposed to this or a similar virus or have been vaccinated, and if we are really strongly immune in a certain way, then body fluids have antibodies. So these antibodies don't break up the virus. What they do is coat the virus particle. But remember that the virus particle is inert. So if it is to grow, then it must be able to make copies of itself. Since it has no biochemical processes of its own, it can only make copies of itself once it gets into one of our body cells. In order to get in, it must stick. And in order to stick, a definite specific protein on the virus surface must stick to a complementary specific protein on the body cell. This is the famous spike protein of the virus and the ACE2 protein on body cells. But if the antibodies are coating the virus particle, if some of those antibodies are also obstructing that part of the spike protein which binds to ACE2 on the cells, then the virus particle cannot stick to cells. If it can't stick to cells, it can't get into cells. If it can't get into cells, it can't set up infection. So here is the first point at which immune responses begin to limit virus growth. As soon as the virus gets into cells, if it sticks, it gets in, it delivers its genetic code into the interior of the cell. The genetic code takes over the cell's own machinery and begins building virus copies. But as soon as the code is released, the code is paired RNA strands. Now, in the cytoplasm of the cell, you don't expect normally that kind of paired RNA to be present. So if the cytoplasm has biosensors floating around which can recognize paired RNA, double-stranded RNA, and be stimulated, because if there is double-stranded RNA, it's not a normal component of the cell and therefore there's something wrong. Effectively, it's a virus sensor. So the virus sensor can recognize viral RNA and start the cell on a stimulated response process. So what does such an infected cell very early on do as an immune response? So it does two things. Number one, the cell itself may or may not be able to do something for itself. But what it can do is, in the area in which it is sitting, it can change situations. Why is this useful? This is useful because all of us tend to think of virus infections as, oh, virus has come into the body, it's all over the body, but it's not. Remember, one droplet has come in, it is sitting at one point in my throat. That is where in a few cells viruses have got there. If virus copies come out of those infected cells, they get into immediately neighboring cells. So there is a locational issue. And therefore, it is the immediately surrounding cells that are at maximal risk. So the thing to do for the infected cell is to signal neighboring cells to be activated and aware. So the first set of signals that an infected cell with an RNA sensor releases are type 1 interferons. And type 1 interferons, again, arm surrounding cells to be resistant to virus infection. Remember, these are as yet uninfected cells that may get infected in the next few hours. But if before viruses reach them, they see interferons, then they will limit virus growth. So this is one way of limiting virus growth. The second way of limiting virus growth is to invite specialized cells of the immune system. So some cells, which are called natural killer cells, get invited. They can recognize virus-infected cells and kill them so that there is no virus growth going on in them. There are other immune responses where what cells of the immune system can do is sample the virus in that location, take bits and pieces of the virus away to regional lymph nodes, which is what we see swollen when we have a throat infection, and generate a specific targeted immune response there. The fact of the matter is that in order for this to happen, cells of the immune response must be recruited to that infected area. And infected cells start by releasing a second group of signals, of protein molecules called cytokines, that generate inflammation locally. And the inflammation has two functions. Number one, it limits virus spread. It localizes, builds a microquarantine zone. And it brings cells of the immune system into this location, so as to kill infected cells, so as to sample infection and take it back and build an actual immune response and then send functional components back to that zone. So this is how the body deals with infections. So there are three categories of immune responses that are built in distant points that are specific to the virus. One, straightforward, that all of us have heard of, is antibodies. So antibodies we've already talked about, and they will coat the virus, they will make it difficult for the virus for a virus particle to stick to a new cell and therefore limit infection, reduce infection. A second immune response that is made is of inflammatory CD4 T cells that contribute to this inflammation, that contribute to the rigor of the microcontainment zone. The third category is exactly like the natural killer cell, only a little more exquisitely precise. They are called cytotoxic T cells. And again, what do? They recognize and kill virus-infected cells and therefore reduce virus growth. This, in broad terms, is how your body, my body, all of our bodies deal with respiratory viruses like SARS-CoV-2.
So you explained the function of antibodies, and that relates to vaccination. So why it is important to get vaccinated as soon as possible?
So as I pointed out, if I have not been exposed to any bits and pieces of SARS-CoV-2, then am I completely susceptible to the virus? Not really. We already went through the proteases, the type 1 interferons, and so on and so forth, all of which are immune responses. So it's not that I am completely susceptible to every new infection. I can be immune. But the virus will grow to some extent. Can I shortcut this? Remember what I said. There are protease enzymes in the fluid. That will help. But if there are also antibodies in the fluid, it will help even more. Similarly, can inflammation be set up at first exposure? Yes, of course. But remember what I said about CD4 T cells aiding and abetting inflammation. If they are already present, then inflammatory microquarantine zones can be set up even more efficiently. Similarly, remember what I said about natural killer cells coming in very early and killing virus-infected cells. But if along with those there are also CD8 cytotoxic T cells very early, then it will be even faster. So if I am exposed to the infection or if I am vaccinated, then an incoming virus infection is even more rapidly and efficiently brought under control. And if that happens, then my chances of having it delayed and linger and take me into severe illness go down. So it helps me individually, but it also helps my community, because if I am limiting both the magnitude and the duration of virus growth in my body, then I am reducing the amount of transmission that I am contributing to. And if I am doing that, then I am not just helping myself, I am helping all of us in a community. Now, can I say that, oh, if I'm infected, then I don't need vaccination? Not really. Why is that? You see, viruses and their hosts like us have co-evolved over evolutionary time. So if we have all these immune tricks to limit virus growth, clearly the virus population must have also evolved evasive tricks. So a natural virus infection, including the coronavirus family that SARS-CoV-2 belongs to, has tricks to limit, delay, evade immune responses. So if I am infected with the actual natural virus, what is the guarantee that there hasn't been some amount of tinkering with my immune response? On the other hand, when we build vaccines, we build mimics of the virus. But the vaccine doesn't have the evasion tricks. And therefore, immune responses to vaccines are more uniform, not necessarily better, but more uniform than immune responses to the infection, quite possibly. And as a result, when you have a good vaccine that prevents hospitalizations, serious illness and death, like all COVID vaccines currently do, then it is absolutely advisable, regardless of whether we have been infected with and had COVID or not, for all of us to get vaccinated, so that we are limiting our chances of getting serious illness. We are also, to some extent, every small amount helps, to some extent, reducing the transmission from us to other.
Sir, talking about vaccination, when I got vaccinated, I was having severe fever and other related conditions, but my roommate was not having fever. So why there is this variation after vaccination about side effects?
So let's ask this question in two different ways. Firstly, why are there these so-called side effects? And I'll explain why I'm calling them so-called side effects. And secondly, what the variability is caused by. So remember what I said. What is a vaccine? A vaccine is a mimic of infection. Basically, we are trying to fool the body into thinking that there is an infection with something that looks like the original virus, so that the immune system will get stimulated and will make an immune response, and that immune response, because it is against a bunch of targets that looks like the original virus, will be useful against the original virus as and when the original virus comes into the body. Now, if we are to fool the immune system of the body is not wasteful. So it does not get stimulated unless something really problematic happens. In other words, unless there is some real possibility of damage, the immune system doesn't just respond to anything and everything easily, at least not in large amounts of response. So clearly, we have to put something in the vaccine that causes a little bit of halchal. All of us will remember since childhood that when we take a vaccine, that part becomes tender, it swells up, there is inflammation. We are building a mimic of an infection. It will, if it does what the infection does to some small limited degree, then there will be a good immune response. All of us get that. There are no exceptions to that. What is that created by? As I said, it's created by cytokines being released locally. Now, some of us make a little more cytokine, some of us make a little less cytokine. All of us will get that local little bit of tenderness, a little bit of swelling, all of that. So all of us will respond by making a good immune response. However, depending on whether some of us have made a little more of these cytokines, the cytokines are really supposed to have a local effect. But if there is enough made, they will overflow into general circulation and then they will have body-wide effects. And those body-wide effects are what lead to fever, that lead to feeling very unwell, malaise as medical people call it, body ache and stuff like that. So that brings me to the variability question. Why do some people have more, some people have less? Yeah. Some of us are 5'2", some of us are 6'2". There is always some amount of variation in the community. All of us are not the same weight, all of us are not the same height, all of us are not the same pulse rate, all of us are not the same blood pressure. Similarly, all of us don't release exactly the same amount of cytokine. So long as the lowest amount of cytokine released is good enough to generate an immune response, that's all we need in the vaccine formulation. But over and above beyond that, some of us will make so much cytokine that it causes what we are calling side effects. Remember, the difference between a side effect and vaccine effects is the vaccine effects are actually part of how the vaccine works. When we refer to a drug side effect, what we are really talking about are effects that we don't want, that are not useful to the actual point of the drug. This is why I tend to use the phrase side effects with respect to vaccine in quotation marks. By and large.
Okay. So, why there is variation in the extent of severity of COVID-19? I mean, some people get severe symptoms and some people are asymptomatic.
So, part of the response to that is very straightforward, what we just said about vaccine effects. There is variation. We have differences in our genetics, we have differences in our life histories, and so on and so forth. But over and above that, COVID-19 and SARS-CoV-2, there is a little bit of an oddity. And that is, by and large, the SARS-CoV-2 infection and COVID-19 as an illness seems to be relatively mild and seems to be relatively localized. There is infection, there is virus growth, there is a little transmission, but immune responses kick in, inflammation happens, everything virus growth shuts down, we get well. In some people, this does not stop here. So, there are two ways of looking at this. One is, let me give you an example. When I cough, there are large droplets and there are small droplets. There is a whole spectrum of droplet sizes that will come out when I cough and I sneeze. Now, a large droplet in the same bout of coughing, large droplets will have large numbers. One large droplet will have large numbers of virus particles. One small droplet will have far smaller numbers of virus particles. In a certain sense, if I have one large droplet that comes and lands in my throat, and I have 1,000 virus particles, or if I have 100 small droplets with 10 particles each that come and land, you will say, I've been exposed to the same 1,000 virus particles. The trouble is, there are two other variables. One is, this large droplet is much more likely to be trapped somewhere in my upper respiratory region, my nose, my throat. The small droplets are very much more likely to go deeper down into my lung tubes. Secondly, the large droplet is landing in only one place. The 100 droplets are landing in 100 different places. In effect, therefore, we are either setting up one large apartment complex as a micro-quarantine zone, or a very large number, 100 small hutment neighborhoods in a crowded basti as containment zones. The consequences can be quite different. This is one level of how illness outcomes can be divergent and variable. A second issue that has been very prominent with COVID-19 is the fact that if all of this happens, this virus comes in, my immune responses from proteases to type 1 interferon to inflammation to antibodies and CD4 and CD8 T cells, everything happens very rapidly, then I bring everything under control. But if there are delays, then the virus spreads a little. So, if the inflammatory processes are delayed, or if the inflammatory processes are a little muted, then the virus spreads a little. More inflammation is built. The virus spreads a little more inflammation is built. Basically, what ends up happening is that even a small delay leads to a sort of not lingering, but slow resolution of the virus growth. And as a result, what ends up happening is that inflammation begins to grow. And if the inflammation is way down in my lung tubes, then it begins to obstruct the tubes. If it begins to obstruct the tubes, if fluid begins to flow in, then my lung function begins to be put into difficulties. I can't get oxygen. I have breathing difficulties. And if the inflammatory cytokines that are supposed to be acting locally keep overflowing into my system, then they begin to have an effect all over my body. And as a result, I begin to get what is called cytokine storm. And then I have all sorts of organ failure issues. It seems, and I'm saying it seems because the evidence is not crystal clear, but it seems that in very many situations, such as people who are elderly, whose immune responses may be muted, or people with severe obesity, or people with type 2 diabetes, or people with atherosclerosis, or similar what are generally called metabolic inflammatory chronic states, all seem to have a somewhat high level of basic inflammation, but a somewhat muted actual response of inflammation. And it's plausible that all of that contributes to this tendency to severe COVID-19 illness.
Yes, sir. So that's all the questions I had. Thank you very much for your time.
Thank you.